I got an email maybe an hour or so ago that there's going to be a pretty nice announcement this afternoon about a nice gravitational wave result. So, early this afternoon. So, very soon.
Does anybody know what it is?
I think, isn't it right now?
12:30.
I think it's right now.
Yeah, it's right now. It's 12:30 to whatever it was, 1:30 or 2 or something. I got the times in Central Time, so yeah.
Is the Redshift schedule just like totally preemptive? How does this talk?
Well, you can cover now.
Seminar. Today, as usual, we have two speakers. First, we have Federica Ricci, and then we have Eric Miller. And before Eric speaks, so Federica will speak about very exciting aging and galaxy collision in the local universe. So Federica is a postdoc at the University of Rome, and she's visiting us for 4 months. Federica came here in July, and she's going to stay until the end of October. And obviously, 306C, something like that. Yeah. So you can all find her. So she did her undergraduate studies at the University of Rome, and then she also did PhD there, and now she's a postdoc, as I mentioned. But during this time, she wasn't only in Rome, but she went to various places. For example, she was visiting here, among other places. She was visiting Southern Canada, and now she's back here for a few months. So her main research interest is AGN, galaxy coevolution. So go ahead.
Thank you for the introduction. So, and for the opportunity of giving the high energy seminar, of course. Today I will talk to you about a project that I have done during my PhD about the AGN galaxy coevolution in the local universe, and in particular on what is the role of type 2 AGN. So we know that almost every galaxy in the local universe hosts in its spheroid a central supermassive black hole, and we believe that almost every galaxy has experienced active phases during its life. We also know from the Sultan argument that the local black holes are the relics of AGN past activity. So the big question is how the AGN affects the evolution of the galaxy where it lives. And in particular, this project tries to understand whether type 2 AGN play a particular role in the AGN galaxy coevolution. So observationally, AGN come in different flavors, but in the 70s, a model was proposed to rule all of them. You are all probably very familiar with the unified model, but I will just say briefly that the unified model describes an AGN as a central supermassive black hole surrounded by an accretion disk. On light days scales, there are the Broiler region clouds that are orbiting clouds photoionized by the central source. All these structures are inside a dusty-shaped element called the torus, and far outside there are the narrow line region. So the direct view of the central engine thus depends on the line of sight inclination with respect to the torus. Therefore, if we can directly see the Broiler region, the AGN will be classified as a type 1 AGN. Otherwise, if the system is seen edge-on, we will only see the narrow lines, and the system will be classified as a type 2 AGN. Inside this scenario, Type 1 and type 2 AGN should have the same intrinsic physical properties, as the only parameter that differentiates the two classes is the line of sight inclination. But there are observational evidences that actually type 1 and type 2 AGN show different properties, as they have different accretion rates and Eddington ratios, different clustering properties, and different luminosities, as you can also see in this plot from Lafranc and collaborators 2005, which shows the X-ray luminosity in the 210 keV band of type 1 AGN, the solid line, and type 2 AGN, the dashed line. Note the differences both in the bright end and in the faint end. So probably one of the most direct and reliable ways to measure the mass of a central black hole inside an active galaxy is the reverberation mapping technique. So if the Brola region dynamics are virialized, then the mass of the central black hole is simply related to the size R of the Brola region and to the width W of the emission line, which is a proxy for the gas velocity dispersion once we introduce a scale factor called the virial factor F, in which we put all our ignorance about the geometry of the system, as always. So thanks to tight radius luminosity relation found during reverberation mapping campaign, now black hole mass virial estimators that link the black hole mass to the so-called virial product are calibrated on reverberation mapped type 1 AGN and widely used in the community. But unfortunately, this type of relations are completely biased against type 2 AGN, which lack the Broadway region width, and we also miss the low luminosity population, since a huge galaxy contamination prevents a reliable measure of the AGN luminosity. And therefore, we can't have a complete picture of the black hole mass function, which is usually computed with virial-based assumptions. And you can see here in these two plots, in the top panel, the luminosity function, in the bottom, the black hole mass function, which are basically the two projections of the black hole mass bolometric luminosity plane, that having a bias in this region at low luminosity and low black hole masses can have a huge impact on our understanding of the AGN phenomenon. So usually the black hole masses of type 2 AGN are measured using the empirical tight correlation observed between the black hole mass and some properties of mainly of the bulge of the host galaxy, such as the bulge stellar velocity dispersion, the bulge mass, and the bulge luminosity. And this correlation has been calibrated mainly on quiescent galaxies and type 1 AGN, but we know that more than a half of the AGN population are type 2 AGN, and we do not know yet if these scaling relations actually work also for them. Moreover, some works have shown that probably the bulge host morphology can have an impact on these scaling relations, as you can see also in these plots from the review of Cormendy and Ho, in which they differentiate elliptical galaxies in gray, classical bulges in red, and pseudo-bulges in blue. The reverberation mapped black hole masses in type 1 AGN are normalized in order to reproduce the black hole mass stellar velocity dispersion relation. So if this relation changes according to the bulge host morphology, then also the black hole mass virial estimators could change accordingly. And you can, indeed, there is a work by Oe Kim 2015 that suggests that the black hole masses in type 1 AGN in classical bulges and in pseudo bulges follow the same relation, but with an offset of 0.4 dex in masses between the black hole mass and the optical virial product. So following this work, we have calibrated a new black hole virial estimator based on the hard X-ray luminosity in the 14195 keV, but also in the 210 keV, and on the Paschen beta full width half maximum. And the advantage is that both the near-infrared and the X-ray luminosity are less affected by reddening and absorption problems than the optical quantities. And again, you can see that the black hole masses in classical bulges in red and in pseudo bulges in blue do follow the same relation, again with an offset of about 0.4 dex with our new virial product. So the advantage of this type of relations is that they can be reliably used to directly estimate the black hole masses in low luminosity type 1, thanks to the hard X-ray luminosity, and in type 2 AGN as well. When the host bulge morphology is unknown, it can be used also an average relation to measure the black hole masses. So the goal of this project is to find broadline region also in obscured systems. But we need to penetrate the obscuring material, and to do that, the near-infrared spectroscopy has been proven to be a powerful tool, as the dust absorption is less severe than in the optical, and moreover, near-infrared spectra of sufficient resolution and signal-to-noise have revealed the broad components in the emission line in the near-infrared. Therefore, we started a systematic near-infrared spectroscopic campaign whose aim was to measure the black hole masses in type 2 AGN randomly selected among the SweetBat catalog, which offers a hard X-ray luminosity almost free of galaxy contamination, and which is complete in the Compton-10 AGN2 population. So we observed our sample with LBT and VLT. Our hard X-ray sample is a local sample up to redshift of 0.1, and with a rough, I would say, a broad range in X-ray luminosities between 41 and 45, which is not bad. Recently, a new proposal at LBT has been accepted, and additional targets are being observed. But up to now, we have collected high resolution and high signal-to-noise near-infrared spectra of 41 AGN2 randomly selected among the SweetBat catalog, and you can see here the spectra split according to the instrument used. So we have found broad components in 13 AGN2, which is roughly 30% of the sample. We have performed the spectral line fitting analysis of the Paschen beta and helium-1 emission lines using Gaussian's functions. We have always modeled the narrow component that you can see always in green in each panel, using a Gaussian whose sigma was fixed to that obtained from a nearby forbidden line. The red broad component, centered at the systemic redshift, not in outflow, is the virialized component that we used to measure the black hole masses. So one of the results of this analysis is shown here when we compare the equivalent width and the full width half maximum of our sample of type 2 AGN in red and for a control sample of type 1 AGN in blue. This line marks the limit for the detection of broad lines in our spectra. So we have found that broad lines in type 2 AGN are less wide and less intense than in type 1 AGN. We have also tested and ruled out biases on the near-infrared broad line detectability against signal-to-noise, infrared and X-ray fluxes, X-ray luminosity, column density as measured in the X-ray, and host galaxy orientation. Basically, everything that we could think about. And moreover, when also optical lines were detected in both classes of AGN, the type 1 that are the black symbols, and in intermediate types AGN that we observed in our campaign, that are the colored symbols, we find an agreement between the near-infrared and the optical measurements in both classes. So with this sample of directly measured black hole masses, we can for the first time see how some properties of the AGN are related to the black hole mass. But first, in this plot, we compare the near-infrared full width half maximum and the hard X-ray luminosity for our sample of type 2 AGN in red for a control sample of reverberation mapped the type 1 AGN, both selected from the SweetBat catalog. Indeed, if we find a difference in this plot, it will naturally show up also in the black hole masses, because these two quantities are the key ingredients of our black hole mass virial estimators. And indeed, you can see that if we concentrate in this bin of X-ray luminosity in which the two populations overlap, we find that the the broad emission lines in type 1 AGN are broader of about 0.25 dex than in type 2 AGN. Here you can see the black hole mass hard X-ray luminosity plane for the sample again of reverberation mapped AGN1 in blue and for our sample of type 2 AGN in red. The black hole masses of both populations have been computed assuming the same virial factor in order to not introduce additional factors between the two populations. And again, in this X-ray luminosity bin, we found that type 2 AGN have smaller masses of 0.5 dex and accrete at higher Eddington ratios at fixed intrinsic X-ray luminosity. So we are seeing these differences at the same AGN luminosity. So what this means? Even though these results are based on a few tens of objects, taken at face value, they do not support an orientation-based unified model, but are rather in favor of an evolutionary scenario in which AGN2 are the preceding phase of an AGN1. They are dust enshrouded buried accreting phase that are naturally less massive and accrete at higher accretion rates until feedback from the accretion disperses the obscuring material, and then the system is visible in the optical as a classical type 1. However, the problem of this scheme is that it has been proposed for bright sources for high luminosity AGN, and there are still lots of uncertainties for the description of low luminosity and moderate luminosity AGN. So we don't have yet an answer. Moreover, if we assume that the type 2 AGN having less than 33 X-ray luminosity were hosted in pseudobulges as we see for the control sample of type 1 AGN, this difference in mass would become even larger. So what I would like to convince you is that the bulgeous morphology can have an impact on the measurement of the black hole mass, and therefore careful bulge disk decomposition is crucial in this job. So now we can investigate directly the AGN galaxy coevolution by seeing the correlation between the black hole masses and properties of the host. Here you can see the black hole mass sigma plane for the AGN2 dataset that are the red symbols, and the type 1 AGN, the open squares, together with some relations from literature. So average black hole masses in bin of stellar luminosities are reported as dark blue for the type 1 and dark red for the type 2. The lower and right panels are the residuals in black hole masses and the velocity dispersion with respect to the relation of Wu, 2013, the dotted, and Cormendi and Ho, the solid line. Again, we have conservatively assumed that both populations have the same virial factor, so that we are not introducing any difference between the two. But actually, there are indications that the virial factor could even decrease at increasing inclination, so that in type 2 AGN should be even lower. Okay. So again, if we consider the black hole mass at fixed bulge property, so at about 200 kilometers per second, we find that type 2 AGN are less massive of 0.9 dex, or almost one order of magnitude, than type 1 AGN, or equivalently, if at fixed black hole mass of 10 to the 7 solar masses, the velocity dispersion is higher in type 2 AGN of about 0.2 dex. Could these differences be ascribed to a contamination in the velocity dispersion measurement? The answer is no. To analyze this, we further divided the active galaxies in early type, the cyan diamonds, and late type, the green triangles. And as both early type and late type galaxies host AGN2 lie below the scaling relations that are valid for quiescent and type 1 AGN, we exclude that the main driver of this difference is the rotational disk contamination. And these results are important, first of all, because we are starting to explore the full distribution of black hole masses, having new data below 10 to the 7 solar masses. It's important to explore the low mass and low stellar velocity dispersion region because it can give clue to distinguish between different black hole seed mechanism. And I should stress also that our results are in agreement with the water masers black hole masses. And finally, these results could imply that the AGN population as a whole could follow a relation with a lower normalization and with a broader scatter. Finally, some work in progress. You can see here the black hole mass 3.6 micron bulge luminosity plane for a sample of dynamically measured black hole masses, basically quiescent galaxies, and for our type 2 AGN. We are following the approach of Sunny et al. 2011, so we are using the software GALFIT to perform two-dimensional decomposition in order to separate bulge and disk components in 3.6 micron Spitzer images. And again, you can see that the majority of our sample of type 2 AGN lie below the scaling relation valid for quiescent and type 1 AGN. So we are starting to demonstrate that type 2 AGN could play a peculiar role in the AGN galaxy coevolution. Should I reply? Do I have... Okay. So just to summarize, we have calibrated a new black hole mass virial estimator that can be used for low luminosity type 1 and for obscured sources. We have detected broad lines in 30% of our sample hard X-ray selected and that we observed during our NearInfrared Spectroscopy campaign. We have measured the black hole masses for this type 2 AGN, and we have found that on average, type 2 AGN harbor smaller black hole masses that accrete at higher Eddington ratios. And finally, we are starting to directly probe that type 2 AGN could play a peculiar role in the AGN galaxy coevolution, as they both lie below the black hole sigma and the black hole bulge luminosity relations. Thank you very much.
Thank you. Oh, questions, yes.
Is our Milky Way galaxy a type 2 seafruit?
I would say no, because there are no I mean, I would not say that it's an active galaxy. It has periodic accretion events, but they are too low to be. I would put a threshold on the Eddington ratio to define a galaxy as active galaxy. And I don't think that the Milky Way is an active galaxy based on this.
I trust you're aware that the photograph or the image made with the SOFIA forecast telescope instrument showed that the Sagittarius A star looks nothing like your model of the type 2 seafruits. I trust you're aware of that. Ryan Lau, in writing the NASA report about this object, saw an asymmetrical three-shaped, three-spiral structure, but did not see the disk and broadline region structure at all.
Thank you.
I have one question. What is the scatter of your M sigma relation compared to the scatter observed for dynamical black holes, dynamical black holes?
So I didn't fit any relation on these points because I mean they are a handful. So I thought it was meaningless to really fit the data. But yeah, with the data that we have, I think that the most meaningful analysis is to say they lie below. This is from a statistical point of view. But yeah, probably they have a broader scatter than type 1 AGN and quiescent galaxies.
Yeah.
So if you go to your summary slide, to the next slide, the very end, the summary one.
Here.
Yeah. So the sample you started with had more than 13 type 2s in it. But you
40,
didn't get
yeah.
to the line of 13. So is it possible that somehow in the selection that the ones that you didn't detect would have filled in the plot in a different way?
We tested different selection
So
effects.
there are some number that were undetected, right?
Yeah.
So if you then go back to...
If you want, there are some selection effects
So
slide.
I'm wondering when you plot the black hole versus... So, yeah.
Here.
This one.
Yeah.
So, you know, the ones that weren't detected, is it possible that there's some selection effect that you didn't detect them, but they would have filled in this plane, they would have filled in this...
Here.
But they would have been on the other side so that the averages would have come out better. Is there some way that could have happened?
Okay. For our analysis, seems that this subsample is a representative sample of Compton-Wick local type 2 AGN. So we don't see any particular trend in or biases. So I don't see how it would be possible that they are overmassive in this plane. I don't have any indication of this. So
For the ones that were missing?
yeah, they are not particular or different from the broad line, the AGN2 with broad line detection and non-detection don't seem different in.
So the absorption doesn't, the absorption distribution is the same, is similar?
So this is the field are the near-infrared broad line detected.
Within, without?
Within, yeah, and without. Okay. So in X-ray, with you see here the column density and the X-ray luminosity, and we didn't see any difference in the NH, for instance, even though we didn't detect broad emission lines with the NH greater than 23.6.7. I mean, they seem, also the averages seems quite similar. Galaxy orientation as well. We tested also that the near-infrared full width alpha maximum has no clear dependence on the NH nor the optical extinction. So we don't see differences. We think that this sample is a representative sample.
Okay, any other questions? In the case, let's thank Federica for the excellent talk again. Okay, until we switch computers, let me introduce our second speaker. So our second speaker is a lot of traveling to do, a couple of stops with the T. So Eric is coming all the way from MIT, and I think he has spent quite a lot of time at MIT, over 10 years, right?
Yes, right. Over 10 years, correct.
Over 10 years, you just say over 10 years. Right? In the meantime, he wasn't only at MIT, but he was also in Japan for a short while, I believe. And then he's very involved in various missions. For example, he is involved in Suzaku, or he was involved in Suzaku, Chandra, and Thome, and what now? What next? You never know.
Yes, that's right. You never know.
You never know what's next. So Eric's main research interest is galaxy groups and clusters and the hot gas in these systems. But today he's exploring a new territory for us. And he's going to tell us about the power of high-resolution fast and asymmetric ejecta in a supernova remnant, whose name you can read.
Okay, thank you. So that's right. The story I'm going to tell you today about this supernova remnant N132D is the result of more than 10 years of work of lots of people, some of whom are shown here. These are the people who actually contributed to the data analysis of this particular research project. But in fact, it really is the contribution of more than 100 of people, many of whom are shown in this picture, working on the Thome X-ray Observatory. Now, this encompassed 4 space agencies and dozens of institutions, which are all listed here. But of course, as all of you probably know, this story has a somewhat tragic ending. And I don't really want to start the talk on a downer, but I do need to explain a little bit about what happened at Thome because the data are a little strange, and you'll see that in a minute. So I've written this story as kind of a 2-act play, and I think a lot of you will be familiar with parts of this, having worked on missions yourselves. So you have an idea for a mission, in this case, what was then called AstroH, and you design it, and you have some instrument that you're very excited about. In this case, it was the soft X-ray spectrometer, which is a microcalorimeter, very high spectral resolution imaging spectrometer. And it should be noted, of course, that the SXS was, in fact, a replacement for the microcalorimeter that flew on Suzaku, but never managed to get science data because the cryogen all disappeared before they were able to start observations. And that itself was a replacement for the microcalorimeter that flew on AstroE, which never actually made orbit. So those people I showed in the previous picture were working on this thing for much more than 10 years. So, and then you start to get excited about what this can do. And this spectrum I'm showing here is a simulation of Virgo centered on M87 for 100 kiloseconds, which shows just the really rich thermal line spectrum that you expect to get from 5 electron volt resolution. Okay, and so you get really excited about the science that happens. So that's the end of Act 1. Act 2 starts with the launch, which for AstroH happened in March of 2016, so about a year and a half ago. And about a week later, the SXS was turned on and the first data started coming down during the commissioning phase. And so several targets were observed, which you can see here. You probably have all read the results from the Perseus cluster, which was the first target observed. I'm going to be talking about the second target observed, N132D. And then there were a number of other targets observed. And then after a month, however, tragedy struck and attitude control was lost and the spacecraft spun itself up and disassembled itself. So this is a tragedy. However, we do have some data from this. Now, I should point out that with the exception of Perseus, all of the targets that were observed were calibration targets or commissioning phase targets. That's not to say there's no science here, but they were really intended for that purpose. And only 2 of them, unfortunately, have rich thermal spectral features. This X-ray binary here has a broadened iron line, but not much else, and the other 3 are really continuum-dominated sources. So in terms of really using the spectral resolution and exploiting it, we're stuck with these 2 sources. Perseus, which has a lot of data. There have been 2 papers published, and there are more coming out within the next couple months. And N132D, this thermal supernova remnant. Now, what was Thome supposed to do, looking at thermal supernova remnants? There are a number of science topics that can be addressed, such as what is the chemical composition and the chemical structure, what is the velocity structure of the ejecta, how much turbulent velocity is there, how does the ion temperature of the ejecta compare with this turbulent velocity and other broadening present. And you can also look for ionization imbalance as well. Now, this is what it was supposed to do. I should point out that N132D itself was not actually in the science plan per se. It was a calibration target, and it was chosen to be an early target because of its line-rich spectrum. Should make a very nice press release. And also, you can use those lines to make sure the instrument is working the way it's supposed to be. Now, that's not to say science wouldn't have been done with N132D, but there might be some other targets that would address these questions better. So, but we have N132D. So I'm actually not going to talk much about the background of the science that we wanted to do because most of it didn't really get done. So I will talk about what we did do. So N132D is a good target for a microcalorimeter because it's a very bright supernova remnant. It's the brightest supernova remnant in the LMC. It's youngish, about 2,500 years old. It's oxygen rich. It's hydrogen poor. It's thought to be a core collapse supernova, a remnant from a core collapse type 1b supernova. In the X-ray, I think there are several people in this room who are very familiar with this remnant. It has a really striking appearance in the Chandra image, which is shown here. It's really brightened around the rim. There's not much going on in the center. If you break this down into the different thermal lines, you see that the softer thermal lines, such as oxygen 8 and iron L and things in between there, all kind of trace that brightest rim area. Whereas when you look at higher energies, which you, until now you could really only do with CCDs, you find that, at least in the XMM, that the iron K emission around 6 keV is all concentrated in the center. So there is definitely a difference between where the cooler components are and where the hotter component is. So the idea here then is that the things producing these lines, these softer lines, are probably emission from the shell sweeping up the ISM as it's expanding, and the emission from the center is probably hotter stuff coming from the ejecta. Some intriguing evidence of that also is that it has these oxygen-rich, fast-moving knots in the interior. So there's evidence for high-velocity material in there as well. And it's a very popular calibration target for soft X-ray instruments. Suzaku has used it, XMM has used it as well. It's a little bit too bright for Chandra, I believe, but Chandra has done some work with it as well. This spectrum over here shows the RGS spectrum, which was acquired very early in the XMM mission. And you can see from this just the really rich, soft lines it has. Now this is in wavelength space. So this is 1.5 keV. So this is the aluminum line. You go down, down in energy as you go up here. So this is, I believe, oxygen 8, and this is oxygen 7. Okay, so everything here is below 1.5 keV. A couple other interesting features of N132D are its local environment. This is, on the left, this is just a composite X-ray image. On the right, this shows the carbon monoxide map of the region around N132D, which shows a really large, dense, giant molecular cloud just to the south of the remnant. And it doesn't seem to be a projection effect because you can see that it appears the remnant is actually plowing into this in the south, where it's blowing out into the north. So, as you might imagine, observing this target as the second target during the commissioning phase presents its own particular observing challenges. And the first one is that the SXS had its gate valve closed. This is just a big door on the top of the SXS door, which prevents, as the satellite is outgassing during the first several months in orbit, it prevents that material from collecting on the very cold filters in front of the very cold SXS. Now, there is a window in this door. This is a picture of the door, but you can see these 4 little quadrants. There's a beryllium window in there, so fortunately it allows some hard X-rays in. However, the beryllium absorbs everything below 2 keV, and the structure that supports it cuts all of the X-rays in half. So you get something that looks like this. This is a simulation again here on the right, which shows for something that's like the Perseus cluster. The red shows the kind of spectrum you would get with the gate valve open, and the black shows what you get with the gate valve closed. This is a log plot too, by the way. So you probably noticed there's nothing below 2 keV, which is where everything in that previous slide, that previous spectrum I showed, exists. So we are not going to see any of these lines at all. That's problem number 1. Problem number 2 is that the attitude was not stable during this observation. So even though it was about a 30 kilosecond observation, the actual time that the remnant was in the field of view of the SXS was only about 4 kiloseconds. This just shows the image from the much larger field of view CCD imager, the SXI, which has a 40 arc-minute field of view. This little box shows the 3 arc-minute field of view of SXS, and that's just a little bit larger than the remnant itself. But for the first 4 kiloseconds of the observation, the remnant was right in the middle of the field of view, and then it slowly drifted away. And then this observation split in half. For the second half of it, the remnant was completely outside of the field of view. So we have a very short exposure. We have also the effective area is cut down by this gate valve so that we don't have any soft X-rays. So this is what the spectrum looks like that we got from those 4 kiloseconds. It has 233 counts in it, which is not very many. The background, fortunately, is low. This is the non-X-ray background now, but that has 23 counts. In fact, the X-ray background is even lower than that. What you can see from this is that you can clearly see a little peak here where iron K is, that has 17 counts in it. And you can see a peak in the sulfur K line, which has 16 counts in it, and probably a peak at argon K, which has 14 counts. So what exactly can you do with it? Well, one thing we can do is we can look at spatially where these counts fall. So the image here on the left, this is just a pixel image. Basically, just it lights up each 30 arc second pixel wherever a photon falls and then projects that into sky coordinates. So the contours here are the Chandra contours. And so you can see in the broadband, there are some counts out here which are probably background counts, but most of them come from the remnant itself. In the sulfur band, you can't really say a whole lot with 14 counts, but they are not exactly centrally concentrated. Whereas in the iron band, they are somewhat more centrally concentrated. So at least this is consistent with getting sulfur emission from the rim, getting iron emission, iron K emission from the center. But what can we do with this in terms of the science that we wanted to do? Well, we can't do ionization equilibrium with 17 counts. We can't do any better on elemental abundances than CCDs have already done with 17 counts, or the gratings for that matter. We certainly can't do spatial structure other than what I've shown here with the 1 arc minute PSF. But we can do kinematics. 17 counts is enough to get a line centroid. So this is what we've done. So what we really need to know, though, is where that line is supposed to be. Because without that, you really can't measure if it's redshifted or blue shifted or shifted at all. And so this is where things get a little complicated. Now, we know that previous X-ray instruments and current X-ray instruments tell us that there are a couple of different thermal components in here that are producing the emission. So the soft emission actually is pretty well constrained to be something like 1 keV or slightly less thermal plasma, and that's probably what's producing the helium-like sulfur line. And then there's evidence from XMM and Suzaku that there's a hotter component with a temperature of at least 2 keV, probably, and that's probably what's producing this iron line. So now there's more recent work, which I'm not going to go into detail, even though it's sort of vital for this, but we can talk about it afterwards if you like, which suggests that this hotter component at 2 keV is actually an over-ionized plasma that's in the process of recombining. And the temperature that we have here for the equilibrium temperature is actually very important, but it seems to be something on the order of 1.5 or 2 keV, and that's the electron temperature. And the ions are now cooling down from the initial temperature, which is something that's not constrained, but it's something very hot, with a time scale that makes it almost in collisional ionization equilibrium right now, but not quite. So the reason that we think that this now, the spectrum shows just the Suzaku spectrum, not including the new star spectrum, is that we see a feature that's consistent with helium-like iron, but we also see this little bump here, which is consistent with hydrogenic iron as well. And so if you fit an emission model to this, either just a collisional ionization equilibrium model or this recombining plasma, you get these sorts of components. You need something that's hot enough to produce the hydrogenic iron, and that gives you lots of helium-like iron as well. Now, the equilibrium temperature determines where that line center is, and I'll show that somewhat a bit pedagogically in the next couple slides, so hopefully you'll bear with me. But we need to really model the iron K complex, so we understand where the line center is supposed to be. So that's what this is showing. The plot on the left shows a very simplified time model of an over-ionized plasma. So at some time 0, when the electron temperature and the ion temperature are the same, there's suddenly possibly a rapid expansion, which produces rapid cooling in the electrons, which cool to some temperature down here. The ions take a lot longer to reach that equilibrium temperature, and that's defined by this tau, this relaxation timescale, I would call it, for recombining plasma. So if we put in an initial temperature of 10 keV and a final temperature of 2 keV and the best fit relaxation timescale that we have, this is the model spectrum that we get. This is a model, so this is not fit with anything. This is photon flux density. And so a couple of things you see here are that you clearly see this that hydrogenic iron line. You see a bunch of lines from helium-like iron, and you see a bunch of lines from lower ionization states of iron. So if we reduce this 2 keV equilibrium temperature to something more like 1.5 keV, you clearly see that the lower ionization states start to take over, and this line centroid shifts to lower energies. And likewise, if you go even further to 1 keV, the hydrogenic iron goes away, and you start to get more and more lower energy lines. You even start to get these satellite recombination lines popping up from lower ionization states. So what you choose for this equilibrium temperature really determines the centroid. For something like a 2 keV equilibrium temperature, the centroid is at higher energy than it is for lower ones. Okay, so this is important if you only have 17 counts. So having said all of that, what we use as the baseline emission model for this then is the result from Ayabamba's Suzaku and NuStar combined fit. And so we have a collisional ionization equilibrium model for the sulfur line at a temperature of 0.8 keV. In fact, this produces the most of the emission in the sulfur line. There's a little bit produced by the second component, which is a non-equilibrium ionization recombining plasma model. And for this, again, we have an equilibrium temperature of 1.5 keV with some error on it. And it's almost in collisional ionization equilibrium, but not quite. The metal abundance in this case really isn't important because, as I'll show, we're just fitting single lines at a time. And we do need to allow for some broadening that's not really constrainable with only 17 counts, but it's probably in there due to not just the thermal width, but probably more importantly, the turbulent width and any sort of bulk motion as well. So I mentioned the particle background is low. It's less than a count in each of these lines, so less than one of the 17 counts is from that. And so we have three free parameters. We have a redshift and a flux. Sigma is actually we're putting a prior on that, so it's an upper limit that we set to sigma for 17 counts. And we overcompensate for the lack of signal by doing a lot of Monte Carlo Markov chains, 100,000 actually for each of the models that we run. So this is kind of in the theory of if you don't know what will work, just hit it with a big stick and see what happens. So here is the spectrum with those 17 counts in it in the iron band. And if you remember a couple slides back, I showed the model which had a gray shaded region, which I can actually go back to. This gray shaded region is what we're fitting. So we're excluding hydrogenic, but only including these lower ionization lines of iron. The data points show the actual counts with real Poisson error bars, so you can sit there and you can count up all 17 if you want to. The blue region shows if we just take that model that we have and fold it through the response of the SXS, which is essentially Gaussian, then apply some velocity to it. In this case, it's the velocity of the LMC ISM in that location, and don't apply any broadening. That's what we get. So hopefully you see that there are 2 points here that are inconsistent with the model. It seems like they're overestimating the model. So in fact, if you fit this with no broadening, but you've just fit a redshift, this is what you get. And you see, hopefully, that it shifted, I'll show that again, slightly to the left. So there's a little bit of a redshift. In fact, it's consistent with 560 kilometers per second compared to the LMC velocity in that location.
What's the significance of this? It can't be more than 2 sigma.
I'm getting to that. Actually, that's shown on the right here. So the right shows the probability distribution. Because we have these 100,000 MC chains, we can plot up, we can really explore probability space, or parameter space, and that's what I'm doing over here. So as a function of velocity on the x-axis, this just shows the fraction of trials that have that redshift. And so the most likely value is here. This is 560. Of course, there's another peak here, which is almost equally as likely, but the central 90% confidence limits are delineated by these dashed lines. So it's more than 90%, but it's not, you're right, it's probably not more than 2 sigma, and it's certainly not 3 sigma away. It's more like 95% away. But it's sort of clear to understand why there are these 2 peaks in parameter space, because you're taking a model that has very discrete features, and you're shifting that against the spectrum that has very discrete features where there are 1 or 2 counts. And so it only takes a few shifts for suddenly the fit to get much better. So that's without broadening. If we include some broadening, this is what we get. And now we're constraining the broadening to be less than 250 kilometers per second. The most likely value hasn't changed very much, but you see that the parameter distribution changes. And now if we allow more broadening, we get a more Gaussian parameter distribution. If we allow even more, it becomes even more Gaussian. One thing I hope you saw is that the center moved to higher redshift, but these error bars got much bigger as well. And I can go back and you can see that. So see, the 90% confidence limits are getting larger as we allow more and more possible broadening. And you probably saw also that the spectrum, the model in the spectrum also broadened out. So in fact, the best fit that we get, and this is from both just minimizing the fit statistic and also from exploring parameter space, is for a redshift of 1,000 kilometers per second from the sun, which is 730 kilometers per second from the LMC, and a sigma of 500 kilometers per second. But you see that's almost within 90-something, 95%, that's consistent with the LMC velocity. Okay, so that's what we get for iron. For the sulfur fitting, again, this is a fairly simple model. This is just collision ionization equilibrium. And I'm showing over here now, this is the model. What's shown in orange is the contribution from the cooler CIE component. What's shown in blue is the contribution from the recombining plasma. So there is a small contribution from this more redshifted component, but it's not very strong. We don't include broadening in here because it's not constrained. When I say we don't include it, we actually allow it. But the best fit velocity is, again, shown here, and it's completely consistent with the LMC velocity with fairly large error bars. And that's what that says. So it's at plus 15 kilometers per second compared to the LMC. But, as I said, this has fairly large error bars. So our interpretation of this is that the iron K emission is redshifted at 700 kilometers per second with 90% confidence limits of 200 to 1300 kilometers per second relative to the local ISM. And this is consistent with the idea that it's ejecta, that it's material that's moving quickly along our line of sight. And that's also consistent with this image that we have from XMM where it's filling the remnant. And it's probably associated with the ejecta as opposed to being associated with the swept up ISM as well. Now, that velocity width that we get can't simply be thermal because that would be much too hot. So there's probably multiple components in there that we just can't simply resolve, that we can't resolve. But it is interesting that not only do we have a large redshift, but in fact the best fit, we also have a fairly large sigma. So there are probably multiple components in here moving at high velocity. The sulfur emission is consistent with being at rest, but again, the error bars are fairly large. However, when you take this along with the images that we've seen of the sulfur band, this is consistent with it being swept up ISM. Now, I know probably everybody in this room has in the back of their head, well, if your emission model is slightly wrong, then this result completely goes away. And that's probably true. We are assuming an emission model here. We're assuming that this recombining plasma is correct, or we're assuming that some material at 2 keV is what's producing this iron K line. So, and we're basing that on the fact that we see this hydrogenic iron line as well. But you can certainly imagine a case where you have some very hot material that just happens to be superimposed that's producing the hydrogenic iron line, and maybe this, what we're interpreting as helium-like iron is a lower ionization state coming from cooler material that's superimposed along the line of sight. We don't have a way of discriminating that right now, so that will have to wait for the future. But assuming that this is the correct emission model, then it seems like we have this redshift result. So I didn't actually mention this, but this redshift is asymmetric as well. We don't see a blue shifted component. If there were a blue shifted component at the same velocity, it would have to be fainter than 30% of the brightness of the redshifted component, which again is possible, but we can't quite constrain that at this point. So we do see asymmetry in other supernova remnants. This is W49b. This is just a pretty picture in multi wave bands. I think the interesting ones to look at are down here. So this is just an image just from the silicon line, an image just from sulfur, and an image from iron K. You can see that there is no iron K emission here. If you read the paper, it suggests that the temperature is hot enough that if it were there, it should emit. And so one idea is that for N132D, if this redshift result holds up, we could be looking at something like W49b just at a different viewing angle. So we're looking at it down the chute, and we see the iron here receding in that direction, but not coming towards us. I hope you look at the title of this slide. That is speculation. We also do see recombining plasma in other supernova remnants, so it's not really a surprise that it could be there, because at the beginning, right after the supernova explosion, the ejecta is expanding rapidly, and those are the conditions in which you expect to get over-ionized plasma. But we really need to understand this thermal model better. I think that the XMM data that exists right now can probably help with that. I know there's somebody in this room who's working on a paper, which will probably help us as well. But I think what's interesting here really is not necessarily the science result, but the fact, and a lot of people in this room know this, that high resolution can produce game-changing science. And we saw this with the Perseus results that came out last year and earlier this year as well. And even in short exposures, even unanticipated ones, they can produce some interesting science as well. Now, I can imagine it would certainly have been nicer if we had gotten more time on this, and 4 kiloseconds probably is the limit of what we can get, what sort of interesting science we can get out. But you can imagine just having a shallow survey of a nearby galaxy where you have some moderate spatial resolution, but you have a wide field and very good spectral resolution, and you don't have to spend very long to get this kinematic information from a number of supernova remnants in that galaxy. So that's just one idea for how this you can really exploit high resolution. And again, I know a lot of people in this room have a lot of experience with Chandra, and so you know that high spatial resolution really changed X-ray astronomy. So we still have to wait in order to get a lot more data with this kind of resolution, but I think we have some opportunities to do that in the future. So thank you.
Thank you, Eric.
Eric, when you showed the beryllium window, how well do you know the transparency as a function of the energy? Because you said half of the photons are absorbed, but I believe that varies a lot, right?
Yeah, it doesn't vary. Well, I don't actually have to go back to it, but I'll go back to it anyway. Yeah, and in fact, there were some calibration questions on this about this right when we were working on the continuum data, really. But it's measured on the ground, and it is actually pretty well known. The thickness is well modeled, and it's calibrated pretty well. So I would say to less than 1% knowledge.
I just want to commend you on this heroic analysis for the 17 photons, 60 photons. It was really, really amazing. To go back to this interesting result that the iron seems to be predominant, the iron ejected seems to be predominantly redshifted.
Yep.
And you can put an upper limit on what the blue shifted material is there. So one idea that you can kick around is, yeah, maybe there is an asymmetric explosion, but you know there's got to be some blue shifted material there, and perhaps the reverse shock has not made it all the way back to that material and heated X-ray temperatures, but it has heated the material that we are seeing. So you can come up with a model like that. So I'm wondering if you have any thoughts on that.
Yeah, that's interesting. I don't actually have any thoughts on that. That isn't something that we discussed, but I think that was also because it could be speculation. But there might be something to think about there, because if you imagine that the part that's hitting the, well, I can go back to this image. Where was it? This. And again, this is speculation, which I hope when somebody publishes their paper will be cleared up a little bit. But you see this bright thing here is actually projected a little bit close to the limb. Now, it's not clear where that is, if that's in front of or behind or in the middle of the remnant. But if you have it, and I do have on the next slide, you know, it's not very far away from where the remnant is impacting this molecular cloud. And I think the evidence is this molecular cloud is in front of the remnant. I don't know if you know that, but I seem to remember that.
Yeah, so you can certainly think that, you know, you can see where the reverse shock,
Right.
the southern part has now made it further back toward the center of the remnant, and what's happening up in the north, the reverse shock has not made its way back to the center of the remnant yet. So that's why you could have this asymmetry in how the ejector are being used.
Do we know? I was under the impression that there was evidence that this molecular cloud, that the bottom part is actually coming towards us, is the closer part, because the molecular cloud's in front of it. Yeah, that was the impression I was under. So that would go against that, because, yeah. So, but that's an interesting idea. You can't say anything with these data, but that's certainly, again, speculation. And I think having some good XMM data would help. There's one up there.
So you mentioned that the background is very low. I mean, that's the particle background. Right?
That's right.
But you do have this extra convenient data set where it's offset. So you could, in principle, figure out what the intergalactic medium might be doing. Have you looked at that? And could that be contributing some of the iron cave?
For the X-ray, no, the remnant is much, much brighter than any X-ray background around there. Yep, it's all coming from the remnant. Now, one thing I I glossed over a little bit, let's see if I go all the way back to the beginning, is that because of it wandering out of the field of view, we actually relaxed the criteria that it has to be in the middle of the field of view. So we're including some times when the remnant was kind of on the edge of the field of view. And that's what these blue things are showing. So in fact, there is some extra background due to that, but it also means that, at all times we're not exactly sampling the same parts of the remnant. Now, with the one arc minute PSF, that probably doesn't matter very much. And for 17 counts, there's no reason to analyze that.
Okay. If there are no more questions, let's thank Eric and Federica.